Welcome to today's explainer. Okay, let's dive right into this. Today we're looking at Competency 002D, which covers a truly transformative process. We're talking about taking students from being just your casual, everyday observers of the world and turning them into rigorous, methodical scientists. We are going to break down exactly how you can facilitate that evolution using systematic observation and structured questioning.
Here is the roadmap for our explainer today. 1. From casual to systematic. 2. Mastering scientific measurement. 3. Generating testable questions. 4. The question funnel strategy. And 5. Science versus engineering practices. Let's get going.
Section 1. From casual to systematic. Building the foundation of observation. You know, in a science context, observation isn't just looking around, right? It's a highly deliberate, planned act. As a teacher, your role is to instruct students on how to accurately record what they see, feel, hear, or measure, but they have to do it without adding their own personal bias. We have to train them to separate what they observe from what they think is happening. And this brilliantly illustrates the two types of data we're dealing with here. First up, we've got qualitative data. This involves observing physical properties using our senses, things like color, texture, and smells. And hey, this is the perfect time to teach vital safety practices, like the proper wafting technique to safely smell chemicals. Then, on the flip side, we have quantitative data. This brings in exact numbers and measurements, like logging the precise height of a plant in centimeters. A robust scientific observation absolutely requires an understanding of both.
To actually gather all this qualitative and quantitative data, students need the right instruments. Sure, direct human senses are the baseline, but as their mentor, you get to guide them to use technology that basically expands those senses. Simple tools like hand lenses, or more advanced ones like digital probes, allow students to access empirical data that is completely hidden from the naked eye. You're essentially giving them the tools to unlock a microscopic or invisible world, turning the unseen into hard empirical data.
All right, Section 2, Mastering Scientific Measurement. Adding precision and accuracy.
Let's move forward and see how this builds over time. Anyone who has ever taught early childhood science knows the relatable chaos of asking a room full of energetic students to measure a desk using a handful of paper clips. But, actually, in those early grades, early childhood through grade 1, we want to use those non-standard units, the paper clips, the little plastic cubes. It builds that foundational conceptual understanding of unit iteration. It's the idea that a measurement is really just repeating a single unit over and over. Then, as students progress into grades 2 through 6, we rein that in a bit and transition them to standard metric units, meters, grams, liters, to align their classroom practices with international scientific standards.
A massive part of teaching standard measurement is instrument precision. Take the meniscus, for example. That's that subtle little curve you see at the top of a liquid inside a graduated cylinder. You literally have to physically guide your students to get right down, bend their knees, look exactly at eye level with the liquid, and read the volume from the very bottom of that curve. It might seem like a tiny detail, but mastering the meniscus is fundamental to scientific accuracy.
Moving right along to Section 3, Generating Testable Questions. From data to inquiry.
Okay, so we have our raw data. But data sitting by itself isn't an investigation, is it? The next crucial step is taking all that bubbling student curiosity and distilling it down into structured questions. A critical teacher skill is helping students realize that, frankly, not all questions can be tested in the classroom. We have to help them focus their curiosity so it neatly fits into one of 3 distinct investigations. Is it a descriptive investigation, where we're just drawing conclusions based on observation? Is it comparative, where we observe 2 different things to see how they relate? Or is it experimental, where we are actually manipulating a variable to see a cause and effect? Teaching students to categorize their questions is an absolute game changer.
Which brings us to Section 4, the question funnel strategy, a classroom case study.
Picture this. You've got a classroom full of students gathered around a large, clear bowl of water. You start dropping different objects in: a metal spoon, a plastic toy, a wooden block, a coin. Some items plummet right to the bottom, while others bob at the top. The students are completely captivated. And, right on cue, you hear a chorus of voices asking, "Why does it do that?" It's beautiful, genuine curiosity. But why does it do that? Is far too broad to be a testable scientific question. It lacks parameters. It lacks a specific focus. So what do you do with this messy, wonderful curiosity?
Now, what's really interesting about this strategy is how you channel that energy. You step up to the whiteboard and use the question funnel.
Step 1, acknowledge the observation of the sinking and floating. Step 2, you guide the students to refine their curiosity into specific parameters. You ask them, well, what is different about these objects? Is it their weight? Is it their shape? Finally, step 3, you funnel that down into a specific testable question. Suddenly, why does it do that becomes, how does the shape of an object affect whether it floats? You've just turned raw wonder into an experimental investigation.
Finally, Section 5, Science versus Engineering Practices. SEPs under the new TEKS.
So the crucial point under the new Texas Essential Knowledge and Skills, or TEKS, is that expectations for student inquiry are clearly divided into two distinct yet complementary practices, known as SEPs. On the science side, this is the pursuit of knowledge. It's all about asking questions to understand natural phenomena. For instance, discovering why a certain shape floats. Engineering, on the other hand, is completely different. It's about defining problems that need solving. It's taking that scientific knowledge and applying it. For instance, designing a boat that can hold a specific amount of cargo without sinking. Science asks why, while engineering asks, how can we fix this?
As we bring this explainer to a close, I want you to consider this. Are you simply answering your students' questions, or are you teaching them how to ask the right ones? Because the ultimate goal of systematic observation and inquiry isn't to turn you into a walking encyclopedia. It's to empower your students with the tools, the precision, and the structured thinking they need to investigate the universe entirely on their own. Thank you so much for joining me to explore Competency 002D. Keep fostering that amazing curiosity, and I'll see you in the next explainer.